Welcome to my presentation for the Manufacturing Technology Conference 2023. My name is Thomas Kleinteich. I'm the head of the X-ray and CT imaging facilities at TPW Prüfzentrum in Neuss in Germany. And my presentation will be about CT imaging of high-tech parts. And thinking of high-tech parts, I think of parts like this one. So this is an additively manufactured metal 3D printed part, so to say. It's a manifold, so it has some hollow tubes. The wall thickness of these tubes is well below 1 millimeter. The tubes have some branching patterns. They are all connected with each other. And so it's really, I think it's a very interesting part because it has so many features to think about. And before you want to use such a part in your machine or in a larger assembly, of course, you might come across topics of quality. So how can you make sure that the part hasn't any material weakness, so that there's no pores or cracks, especially in critical areas where you might attach the part to other things? How can you make sure that the hollow tubes are leak tight? How can you make sure that the internal channels aren't blocked, for instance, by powder that is used for the additive manufacturing process? Also, you might think about shape deviation. So you have to be sure that the part has the same shape as you designed it, just to be certain that it can be well aligned with other parts or can be assembled with other parts into larger structures. And especially for those kinds of parts that have a very thin wall thickness, that might be already at the limit what is possible in terms of manufacturing. So you might want to ask, so is the wall thickness everywhere as I would have it expected as I designed it? So well above the minimal wall thickness for a given part. And if you thought about these things in the past, you already might have come across industrial computed tomography. Often this is referred to just as CT, or I always prefer to call it CT imaging, because imaging says what it is. So it's a method where we generate images, an imaging method. And my presentation will be about CT imaging, and I will explain how the method works. I will talk a little bit about limitations of the method, and finally show how these questions that I just printed on the screen can be answered by using industrial computed tomography, or shorter CT imaging. But before we start talking about CT imaging itself, we need to talk about X-ray inspections. This is because CT is a kind of X-ray inspection. So everything that applies to X-ray inspections, or to X-ray imaging, so to say, also applies to CT imaging. So it's quite important to keep some basics on X-ray imaging in mind when talking about CT. And what you see here is a rough setup for an X-ray inspection. So we do have a part that needs to be inspected. We place an X-ray source to one side of the part. An X-ray source can be an electronic X-ray source, but could as well be some radioactive isotope. And on the other side of the part, we place an X-ray detector, or in the more classical way, we place a film behind the part that is exposed to the X-rays. Now, the X-rays from the X-ray source will pass through the part, and parts of these X-rays are being absorbed by the part. And what you then capture on the film is kind of like a shadow image of the part as the X-rays pass through this part, and this shadow image is called an X-ray projection. So it's like the shape of the part projected onto the film or onto the detector. Now, if your part isn't an industrial part, but is a dog that might have swallowed a keychain, the resulting X-ray image will look something like this. As you said before, X-rays are being absorbed while they pass through the object, in this case the dog, that you would like to inspect. And now the important thing is that materials differ in the way in how well they absorb X-ray radiation. So you see the keychain in this case that the dog might have swallowed is made from metal, and so it has a much different contrast than, for instance, the skin or the muscles of the dog that appear more or less fully transparent. And how much X-ray radiation is absorbed by different materials is first depending on the atomic numbers of the elements. So this is when you talk about the metal keychain. So the atomic number of iron, for instance, it's much higher than the atomic number for calcium, that would be the bones, or the atomic number for carbon, which is mostly the skin and the muscles. So this is why the keychain has a much brighter appearance on the X-ray film than the soft tissues. And of course, besides the atomic number of the elements, it also depends on material thickness. So this is much more intuitive, I think, as you can easily think of having a very thick part. It's much harder to have it penetrated by X-rays than having a very thin structure. Now, these two things, atomic number of elements, so what kind of material you're actually looking at, and the thickness of the material are the key issues when talking about X-ray inspection. And it has a very big impact, especially when thinking about industrial X-ray imaging or also industrial CT. What you now see on the screen is that the corresponding wall thickness for different common metals that are used in industry, like aluminum, titanium, and steel, for X-ray inspections at identical X-ray power. So if you use the same X-ray settings for aluminum, for titanium, or for a part that is made of steel, 30 millimeters of aluminum correspond to only 5.4 millimeters of steel. So it has a huge impact if you're trying to study an aluminum part or if you try to look at a steel part, because you will have less contrast in the steel part, you will have a poorer X-ray signal because of much higher X-ray absorption of the material itself. And there's one more thing to keep in mind when looking at these X-ray images. You always have to be aware that these X-ray images are only a 2D projection of the full geometry into one single plane of view. And well, as said before, this is a picture of a dog that swallowed a keychain. However, just based on the X-ray image, if you don't know the dog and if you haven't seen the dog in itself, if you only know the X-ray image, you will actually not be able to tell where this keychain is. So the same picture you would achieve if you have a dog and that hasn't swallowed the keychain, but where you place a keychain just outside the dog and take the picture from that side. And so in case the keychain wasn't inside the dog, but it was like on the side of the dog, you actually also cannot tell from this picture if the keychain was in the front or the back of the dog in this picture. So you have no information at all on the position of the structures you're looking at, depending on the plane of view, depending on the orientation of the object for the X-ray image. And that's a really difficult topic, and that's something that also applies to industrial parts and industrial X-ray inspections, of course. So here you see another additively manufactured manifold. It's made from aluminum. It's a quite large part, and you see it has a complex geometry. And if you look closer, it's the same as with the keychain and the dog that I just explained, where you have no information on where the keychain is on the dog. You have the same issue with the drill holes on the bottom of these parts. So drill hole 1 and 2 are lying on top of each other, as well as drill holes 3 and 4 are also lying on top of each other. So if you cannot really tell in such a part where there's really large drill holes, where exactly the position of these drill holes is, you will have no information if you find any voids in this region. So you might be lucky and see these voids beyond all the geometric features that you also see in the image. But even if you find those, you cannot tell if they are like in between these two drill holes, if they are in front or behind those. And for many applications, this can be an issue. And so it's desired to not have some 2D information, but to have 3D information on the part. And the most simplest thing to move from 2D to 3D would be to look at the part from different orientations. So basically to capture X-ray images of different views of the part. And this is exactly the principle that is followed by CT imaging. So this picture might seem familiar to you, because this is basically showing the setup for the X-ray inspection. But now I will start talking about CT actually. And CT is exactly the same setup as we used for the X-ray imaging, but the big difference is that for CT, the part is being rotated. So what we capture on the detector, in this case, will be X-ray projections of a rotating part. So one can say CT is X-ray imaging of a rotating sample. And this is what an industrial CT system that we have available at TPW Prüfzentrum looks like. From the outside, it's more or less a big box, and it has to be a closed system like this because, as I said before, it's working with X-ray radiation, and one has to be sure that there's no X-ray radiation contaminating the outside of this machine, so that it's safe to work with these machines or that they have them in a safe environment. Then if you open the sample chamber of the CT and you look down into the machine, it basically looks like this. It's lots of technique, and if you then turn around a little bit and then look from the different angles, this is what you see. And what you see here in this picture are the three main components of the CT system. So there's the X-ray tube to the right, there's the sample stage in the center, and here on the left is the detector that captures the X-ray image. And so remember, this is the setup that I showed you before. So we do place the sample on the sample stage is rotating, the X-ray tube is generating the X-rays, and the detector will capture the pictures of the rotating sample. And this will basically look like this. So this is the kind of data you get out of an X-ray CT machine. So you get X-ray images of a rotating sample. Now, if you look at the sample and pay attention to it, you already might get a very good understanding structure, even though you may have never seen this part before. So just by rotating it and by looking at it from different orientations, you get some good understanding on what the 3D shape of. And now for CT imaging, when we look at the CT data, we do not want to look at thousands of X-ray images from different orientations. We have a 3D model of the part, a virtual 3D model of the part. And this 3D model is calculated or reconstructed based on the X-ray images of the rotating sample. And so this process is called reconstruction. The algorithm is called filtered back projection. So basically from the projections we go back to the actual part and generate a digital version of the actual part on the computer. And now this 3D volume, the CT data set, that's the kind of data, if you ever worked with CT, that you will be most familiar with. So this basically corresponds to image stacks that you can slice through any direction you like. So you can go from top to bottom, you can go from front to back, you can go from left to right. So you can really generate thousands of images through the part without actually taking the part apart, because you're already working on a digital version of the part that you only have on your computer. And what for the example of this larger manifold, a slice movie would look like. So basically going from top to bottom of the part, and you see all of these structures inside the part. And what I really want here is that this is not the representation of the CAD model of the part, but this is the representation of the actual part that was scanned by using X-ray images of the rotating sample. The important difference is that in these slice images, so that's not the perfect part, but that's the actual part with all its imperfections. So that's a very powerful tool to study those. To the questions I raised at the beginning of the presentation, where I talked about lead tightness, material weakness, shape deviations, wall thickness, blockages. And already said that this can be answered by using industrial computed tomography. So now, of course, if you have a CT scan of such a part, of this manifold, you can place planes of section in regions where you are concerned about potential weaknesses. It might be caused by foreign material inclusions, by porosity, by cracks, whatsoever. And you can look at the section images at those regions and say, well, okay, here everything looks fine within the resolution limit that I have with the CT system, and I could spend another presentation just talking about this, but within the resolution limit of my system, I cannot detect any porosity, any void, so I think I'm really safe in this position to say so there's no material weakness. And you can do the same for other regions as well and check if you see any pinholes in the walls or if you see blockages in the internal channels. And of course say, well, okay, I checked, so I can be sure this part will be leak tight. I haven't seen anything that is blocking the channels, so I can be certain that the channels are free. And so you can check these from your list of quality topics. And of course, talking about shape deviations, one thing what is commonly done is doing false color representation of shape deviations of the part geometry versus its nominal geometry that is defined by the CAD file. And so this, of course, can also be done based on CT data, because with the CT scan, you capture the full 3D geometry of the part with all its internal and external features. So it's very straightforward to compare this against the CAD file and to visualize these deviations by using false color coding. So you can also take the shape deviations from your list of things to check. And finally, wall thickness, and you might have already guessed it, there's also possibilities to automatically measure the wall thickness throughout the entire part geometry and to return it, and also to have some false color coded representation that in this case does not show shape deviations but shows a false color coding of different wall thicknesses, and you will immediately see if there's like critical regions where this wall thickness drops, and you can have like measurements all over the part to study wall thickness. So you can take this from the list as well. So in summary, you now have a very complete, a very comprehensive picture about the quality of the part you want to use, you plan to use in your machine. Now, finally, for the last minute or two, some words on what we as TPW Prüfzentrum are doing. So we are not a company that is developing CT software or that is developing CT machines. And so you cannot buy software or machines from us. But what you can do from us, or what we do, is we are a service provider and we provide CT inspection service to our customers. And besides CT inspections, we also have other inspection methods from the destructive and non-destructive fields of inspection. We're a DAX accredited testing laboratory. We're placed in Neuss, which is close to Düsseldorf in Germany. And Now, as a service provider for CT imaging, we have the expert knowledge on CT and X-ray related topics. So before you even start a project, or if you have a particular part and you are interested in the possibilities in how to inspect it, and of course in the end it's often also a question of costs and lead times, we will consult you on the application of CT, considering what we know about the physical and technical limitations of the CT imaging method. And of course we also do the CT scans. In case you can provide us with a clear specification on what would be okay or not okay for your part, we can also evaluate this CT data and give a report with the part and say it's okay, it's within specification, or you can say it's not okay, it's out of specification. But we also have several customer projects where basically the customers are more or less interested in just looking inside to see what it's like, if the assembly is correct, if there's any potential issues. And so in these cases, the customers will look at the data themselves, and we then provide the consulting on the interpretation of the CT image data. So we help our customers to understand these images, to differentiate between what is real or what might be imaging artifacts, so that the customers get a good understanding on how the method works and also on what to do with the data that we provide. And with this, I'm at the end of my presentation. I thank you very much for listening and for watching. If you have questions, feel free, of course, to visit our booth or reach out to me at my email address or my contact information, which you see here. Thank you very much.